Alrighty, thank you so much for joining us today. We're excited to have you on our webinar today to talk about stream restoration at the Stibnite Gold Project. We have one presenter today, Rob Richardson with Rio, and I'm going to go ahead and let him introduce himself in 1 second. We are going to go through this entire presentation and leave Q&A to the end of it. However, I do encourage you to go ahead and put in your questions in the Q&A box that you can find down at the bottom of your screen at any point in time during this presentation. And we'll make sure to get to as many as possible when Rob is done presenting. So with that, Rob, would you like to introduce yourself and get started?
Sure thing. Thank you, Shelley. My name is Rob Richardson. As Shelley mentioned, I work for Rio Applied Science and Engineering here in Boise, Idaho. We are a small engineering science firm that focuses specifically on river restoration. That's 100% of the work that we do. And we've been working for Perpetua at the Stibnite Gold Project site for going on 4 years now. So quite a while. And our principal role is, of course, helping develop a restoration plan for the streams that would be impacted by the project. So I want to walk you through our stream restoration plan and how we've gone about putting together our stream design and evaluating the potential impacts and benefits associated with that to hopefully address the habitat needs up in that neck of Idaho. So let me walk you through this. Make sure this thing's working here. All right, so the project area, as many of you probably know, sorry, I've got to minimize my pictures of everybody. So everybody probably knows is sort of in the geographical center of Idaho. So we're east of McCall and Cascade, about 84 road miles from Cascade. So it's out there a little ways near the town of Yellow Pine and in between Yellow Pine and the Frank Church River of No Return Wilderness. Like I mentioned, I'm going to be focusing on the restoration of phase of the project and specifically our stream design. There's a large wetland restoration, upland restoration component as well. Our role is very focused on the stream restoration. So I'll be walking you through information that is part of our stream design and associated stream design report that's been included as part of the environmental impact statement, draft environmental impact statement for the project. So the goal, which I'm just going to read real quickly for our stream design, is to reclaim and or restore disturbed streams and floodplains from both historical and proposed mining activities to improve habitat conditions for aquatic species and mitigate for project impacts. So I'll get into this a little bit in a minute, but first I wanted to go over some nomenclature. So the project, the Stibnite Gold Project, is a mining project. And at the end of the proposed mining operations for each individual facility, that facility would be reclaimed. And often the stream is considered reclaimed at that same time. And Perpetua is committed to a restoration standard whereby, in addition to reclamation, there would be restoration of the streams on top of those reclaimed facilities. So I just quickly wanted to explain, at least using language that's meaningful to me, what the difference is. And so here's an example. The photos in the background are real examples of the Yankee Fork of the Salmon River in Idaho. That area had been placer mined and then reclaimed. And you can see the image on the left. You have a relatively stable, static, relatively low quality condition that doesn't really deform or change over time. And then the restoration, so that reach actually, there's a number of efforts to restore the previously reclaimed portions of that stream to provide for a more dynamic, naturally functioning and resilient stream channel. So the image on the right is a fully 100% constructed river. All of the banks and the large woody debris you see, the riffle in the background and the pool in the foreground, all of that was constructed as part of a restoration effort, following a natural restoration design process. And so talking from here on forward about restoration of the Stibnite Gold Project, that's what we're going to be talking about, is the image on the right. All of our stream designs follow the natural stream design process in an effort to best mimic natural conditions on site. So a couple examples of projects that we've completed over the years, just to kind of show, what does this look like a few years after restoration? Obviously, it takes some time for the vegetation to grow, but because you're right there in the riparian area, it does grow relatively quickly compared to upland areas. So here's an example of Catherine Creek. This is a tributary to the Grand Ronde River in eastern Oregon near La Grande. And so this project included a complete channel reconstruction. The whole channel and floodplain was constructed from scratch. And so everything you see here was placed by a machine and built and planted. But 3 years after construction, you can see the riparian vegetation is really starting to take hold and take root. And in short order, it'll start to provide shade, and over the long term, ultimately large woody debris recruitment. And therefore, in the short term, you can see some woody debris has been placed for habitat and structure. But just a couple examples of what a natural stream design actually looks like after it's completed, which is very different from a reclaimed stream that is often lined with riprap and other armoring features to prevent any undue erosion and provide a lot of stability. All right, so focusing in on the Stibnite Gold Project, I have an image on the right. Just a reminder that the streams generally flow from south to north at the project site. Our stream design objectives then for the project include providing fish passage above Yellow Pine Pit. And I'm going to get into that here in the next couple of slides. Restoring high quality stream channels over the top of the proposed mine features. As I mentioned, the Stibnite Gold Project, of course, would expand and create some mine features that the stream would be diverted around during mining. And then after the mine feature has been reclaimed, we would restore the stream, basically reestablish that stream back over the top of that mine feature, following that natural stream design process that I mentioned. Meanwhile, there are a number of stream reaches that have been historically impacted that are not proposed to be impacted directly by this project. But because they're not functioning at their highest potential, we're also proposing to enhance the habitat along many of those stream reaches by adding things like large woody debris and boulder clusters and pools to enhance the habitat conditions there. And then combining all of that information to evaluate the net ecological benefit. As I mentioned, as part of the goal is to increase the net ecological benefit as part of this restoration effort. We've developed a stream functional assessment. I'll end the presentation talking through how we've evaluated the impacts and the restoration benefits to essentially evaluate that net ecological condition. All right, kind of a busy slide, sorry, but just wanted to walk folks through the 3 different phases of the project. So on the left, we have the baseline condition. In the middle, we have interim or during mining, and on the right is the restored condition. And these are, the image on the right depicts I think it was the alternative 2 from the draft EIS. So keep in mind, we're in the draft EIS process, so everything's a little bit in flux as a preferred alternative is being identified, and improvements to the project are being made, or refinements, I should say, associated with feedback through the EIS process. On the left image, the baseline, you can see the yellow polygon represents that area that has been historically impacted. So this is in the Stibnite mining district. There have been active mining going on here for about 100 years. And so the yellow area represents areas that have been historically impacted. It's about 8.3 miles of perennial stream are directly impacted or lie within that yellow polygon. The Stibnite Gold Project, at least the alternative 2 that was proposed in the draft EIS, shown in the middle is the blue polygon, and where it overlaps with the yellow, we've got yellow and blue makes green, so that's that green area. You can see the project largely overlaps the existing historical impact areas, but also is expanded in a couple of watersheds, particularly, if you can see my pointer here, this is Fiddle Creek. I should note that as part of the refinements in the draft EIS, much of this Fiddle Creek impact is proposed now to be removed from the mine plan, but then also farther upstream into, this is the Meadow Creek watershed. But notably, there's a large overlap between the proposed impact and the historical impact. You can see some of those yellow areas persisting, particularly along the main stem of the east fork of the south fork of the Salmon River. And these are the areas that I mentioned earlier we would propose to enhance. They're not proposed to be directly impacted by this project, but they have been historically impacted. So that's about 12.2 miles of impact associated with the Stibnite Gold Project, directly impacted perennial streams. And then the restored project, again, we've got mine features that would be reclaimed and stabilized, and then streams restored over the top of those features. It's about 12.6 miles of perennial stream. So that's an overview of the overall project. Now I want to get into a little bit of detail about our stream design process, what actually goes into developing our stream design. Then a few examples. I'll show you the Yellow Pine Pit, this area up here, it's called Blowout Creek, and this tailings storage facility. So give you an example of what our design actually looks like in those three areas. All right, so first of all, current conditions at Yellow Pine Pit. So this is an example or photo, sorry, of the existing Yellow Pine Pit as it is today. You can see the east fork of the south fork flows in from the right down a cascade, which is currently a barrier, and then flows through the pit and out. You just kind of see it flowing back out and down valley. So a significantly impacted area. And notably, this cascade flowing in is a barrier to all migratory fish. So some migratory bull trout, but most notably Chinook salmon and steelhead that would otherwise spawn upstream of here, go out to the ocean and come back. So those fish have been blocked from upstream habitat for about 80 plus years. During the historical mining period, the Yellow Pine Pit that created the barrier was mined, and to provide, to reduce the amount of water entering the Yellow Pine Pit to allow for the mining, a tunnel was built to divert water around the pit. Well, Perpetua is proposing something similar for the expanded Yellow Pine Pit as part of this project, but the tunnel itself would also have a fishway within it, essentially a fish ladder like you would see at a dam, but because the gradient of the stream, and we're looking at a sort of cartoon layout of what that would look like, flow is coming toward us in this image, you'd have about a 0.8 mile long tunnel or 0.9 mile long tunnel that has a series of weirs allowing fish to pass, because the gradient of the tunnel wouldn't be so great that fish would not be able to pass. So the idea being that you provide access to fish early on during the mine life, because there's a lot of habitat upstream of the Yellow Pine Pit that's currently could provide very valuable habitat. It's just not accessible. So that's the during mining phase. And I'll talk about that's, in operation for 7 to 10, 12 years. And then the Yellow Pine Pit actually would be backfilled, and our restoration plan includes restoring a stream over the top. So this tunnel is a temporary measure to allow early access for fish in areas upstream. So what's upstream of the Yellow Pine Pit? So I'm looking, north is up in this image, so all the streams are kind of flowing up, and the Yellow Pine Pit is in this area where the black arrow is pointing. And you can see there's about 35 miles of perennial stream located upstream of that point. And not all of those streams are large enough to sustain fish, especially the larger fish like Chinook and steelhead. But somewhere on the order of 6 to 7 miles of that habitat upstream of the Yellow Pine Pit barrier would be suitable for Chinook and steelhead spawning. And so we're proposing to provide enhancements, as I mentioned, to some of those reaches, and then restoration to others. And what you can see in this image, the dark blue represents what would be accessible as after the tunnel goes into place and or the long-term restoration over the top of the Yellow Pine Pit. And then whereas all of this was previously inaccessible, this uppermost portion of Meadow Creek would be the only inaccessible portion after that point. So the objective, of course, is increasing the access to existing and enhanced or restored habitat. So what does some of that habitat look like? The existing habitat in the upper watershed of the East Fork and the South Fork of the Salmon River looks pretty good, which is why it's beneficial to provide access to that sooner rather than later. So it's kind of broken out into two areas. The area on the left, as you can see, there's a bunch of large woody debris because that area had burned several years ago, and those trees are now starting to decay and fall into the stream, and allow for recruitment and storage of gravels and creation of pools and really nice habitat for resident fish, as there are some small resident fish populations that persist upstream of the barrier, just no migratory fish. And then once you get above the burn area, you enter into a predominantly spruce fir forest that you see on the right-hand image with nice undercut banks, gravel stream bed with pools and riffles, and really relatively high quality habitat. So that's existing today that the migratory fish currently don't have access to, that the tunnel and the later restoration would provide access. The rest of the area is area that I've mentioned would be restored and enhanced. And so that's where I want to walk you through our stream design process a little bit and show you a couple of examples. So the process that we go through is the same for every stream design project we do, whether it be for Perpetua and at a mine, or whether it's for a land trust or a nonprofit or whomever elsewhere in the state of Idaho or somewhere else. And the first step is always a reach delineation. We take the project area and break it out into areas that are geomorphically similar, have similar form and function. That way we can fine tune our stream design for each of those individual reaches rather than something that's generic and maybe not appropriate at that finer scale. So you can see on the right all of the different reaches that we've established for this particular project. The next step is reference site analysis, and that leads directly into the development of our design criteria. So I'm just going to kind of jump to the design criteria and talk about our reference site data there. See the map on the right, the project area is highlighted in that little red rectangle. You can see where yellow pine is located with the red dot. So we've gone in and around the project area and identified a number of reference sites. Now, the reference sites don't necessarily represent ideal conditions. They represent a variety of different natural conditions that are currently expressed on the landscape so that we can compare and contrast with areas that we're proposing to develop our stream design and try to pull some of the best, most functional characteristics from those reference sites and emulate those in our design. Meanwhile, not duplicate those components of the reference sites that are not functioning as well. So those reference data, then some sites are particular to certain reaches. You can see the table there in the bottom right. Certain reaches have various reference sites that we use to provide those reference data. As an example, here's one reference site. This is Reardon Creek. This is one watershed to the west of Meadow Creek up at the Stibnite Gold Project site. And interestingly, Reardon Creek, and fortunately for us, it's right here in the project vicinity. There's a lake, as you can see in the image on the upper left, Reardon Lake, and it was formed by a large glacial era landslide. So several thousand years ago, a large landslide dammed Reardon Creek, backed water up, creating a lake and a very nice forested wetland meadow, which you see in the bottom photograph. We have multiple reference sites in Reardon Creek to help us identify and emulate those really nice high quality habitat features formed in this low gradient meadow upstream of the dam, the landslide dam. Because one of the project features associated with the Stibnite Gold Project is the tailings storage facility, which consists of a large dam and rock buttress, and then a very low gradient stream restored over the top. So you can see, for example, these are all the same scale, these three graphs on the right. You can see Reardon Creek, and you can see this landslide represents a relatively steep portion of the stream gradient. And then you have this very low gradient segment upstream that represents the lake and the wetland meadow. So those were excellent reference conditions for us. Similarly, the project site was historically glaciated during the last ice age. And there are a number of reference sites similar to that throughout Idaho. Most noteworthy, I think, is the Sawtooth Valley. So I just pulled one example from the Sawtooth Valley where we have Hellroaring Creek, which was dammed by glacial moraine. So you have a steep gradient associated with that glacial moraine, and then a very low gradient stream segment on top. So again, really nice reference that we could use. And then the proposed project, we have a steep gradient associated with the tailings facility, and then a low gradient on top to where the stream would be restored. So one example of where we've used reference conditions to help us develop our stream design. Now, in addition to the reference site data, we use empirical formulae that we develop. So the reference data represent points sort of in and around the project vicinity, and they may not be exactly duplicative or representative of what we're trying to design. And so we have to sometimes fill in the gaps between the points. So we'll use statistical regression analyses and other things to develop these empirical formula to fill in the gaps. So I'll show you some examples of that here in just a minute. And then lastly, published design guidelines. There are numerous published design guidelines, not least of which are the watershed conditions indicators developed by the Forest Service for this area specifically. We have a number of guidelines that help us identify the sort of ideal or targeted number of pieces of wood per mile, for example, or pool frequency, or channel width to depth ratio, those types of things. So those all get pulled together. In the image you see on the right, we've produced a sheet for each one of our project reaches that represent the targeted geometry for that particular reach based on all of those design criteria. So digging in just a little bit deeper on the design criteria, how we go about actually kind of pulling all of that together. It starts big picture where we look at the sort of geomorphic function of the stream. And again, here's a picture of Reardon Creek, one of our reference sites. And similar to Reardon Creek and that low gradient area, we've made an assumption based on information from past projects, from project partners associated with this project and others, and from habitat information at the Stibnite Gold site, that the lower gradient stream reaches are those that possess the greatest potential for habitat, particularly for spawning Chinook and steelhead and bull trout, and west slope cutthroat trout, which are the key species that we're concerned with. And so we've made an effort to try to, where it's geomorphically appropriate, to recreate those relatively low gradient, high quality stream habitats. So to do that, we've taken those reaches that are otherwise steep, like the dam buttress at the tailings facility, and actually steepened it. So by doing that, we've reduced its area and increased the relative area that's available for the lower gradient, high quality habitat. And thereby we can create these sort of meadow-like conditions in those lower gradient reaches. And then of course, add habitat features like large woody debris, boulder clusters, rock pools, and such to increase the habitat within those sites. So once we've identified what the objective is for a particular reach, then we go about developing the actual physical design criteria for that reach. And I'm not going to read these to you, but you can see what the general criteria were for the reaches that we were working with up at the Stibnite Gold Project. Essentially, we calculate a floodplain width, and that one is, frankly, I think the most important, because there are a number of regression equations and reference information, both in the literature and from reference sites, to be able to calculate this belt width, or the maximum amplitude of a potential channel as it migrates and creates those bends. And as each bend moves and migrates, those have a sort of maximum amplitude that they can expand before they start doubling back on themselves and cutting off those bends. And that maximum amplitude represents the amount in which that channel might migrate. And we want to make sure that we're designing a floodplain that's at least as wide as that maximum amplitude. So you can see we've designed all of our floodplains to be 125% to 200% the size of that maximum amplitude. So following our natural stream design philosophy, we want to make sure that the stream has ample room to migrate, meander, avulse, be dynamic and change over time. And then of course, we have the channel capacity, we have to develop the bankful width, depth, and all of that. And again, I don't want to read all of these to you, but essentially we go through and using data from empirical data from real world sites, come up with the appropriate channel geometries from which to build the new stream within that broad floodplain. On the right here, you can see some of our regression examples where we've gone through and calculated, essentially filled in the gaps between data points. We're very lucky on site. We have a lot of really high caliber, high quality hydrologic data. So there are a couple of USGS gauges on site, as well as other gauge data that have been collected over the years, and regional gauges. All of that information can be compressed using statistical analyses that were developed by the US Geological Survey to calculate the estimated discharge at any point within the project area. So we've been able to estimate what calculate what low flows and sort of moderate high flows and even severe 100-year, 500-year floods would look like at any of our reaches, and be able to evaluate the hydraulics at each of our stream reaches that we're proposing to design to see, how much sediment, what grain size sediment would we expect to move, and how what needs to be done to make sure that the banks are appropriately stable but not overly armored so that they would never migrate. So we're fortunate to have that good hydrologic data and to be able to inform our hydraulic analyses. And some of our reference sites we also use to essentially calibrate our data, so we can back calculate the results at a reference site and make sure that our regression equations match the real world data that we measured at those actual reference sites. So we did that to calculate roughness, for example. The bottom right image is a Manning's N value, or a roughness estimate that's really important in calculating hydraulic conditions within a given stream segment, and sediment transport as well. And so we've been able to calculate and estimate all of those things, then apply that to each of the different stream types that would be constructed as part of the project. And so there at the bottom, I'm just showing the different stream types that we've identified. And the last step of the physical design process then is to ensure that you have the appropriate stability along the bank for each stream reach. Some reaches are steep and they need greater stability. Others are less steep and need less stability. As I mentioned before, with the natural stream design, we're proposing, a dynamic system that it generally includes bioengineered stream bank materials rather than, riprap or concrete or something like that. So here's an example of a low gradient system where this is an actual stream that we built on the photograph on the bottom, and the sort of engineered typical drawing on the right of that feature. It's a fabric encapsulated soil lift. You basically take a biodegradable coir fabric that's made out of like coconut fiber and wrap soil inside of that to help retain that soil, because there's obviously no rooting structure to help hold the banks in place on day one after construction. But then you plant that with willows and cottonwoods, or in the case of the Stibnite Gold Project, it'd be alder and willow and spruce trees, but then also sedges and rushes that can grow quickly and create an immediate or near immediate rooting structure. So you can see on the image on the photograph, that's just 1 year after construction. You can see all the sedge already growing through. You can just barely see the coconut fabric kind of sticking out here and a little bit into the stream itself. But just an example of, we go through every reach and identify what's an appropriate bank treatment to make sure that we have stability year one. And then it's appropriate plantings are established and prescribed for each reach, so that ultimately the riparian vegetation would take over and provide that stability as these features that we've installed slowly decompose over time. And then on top of that, we add habitat features like wood and log jams and things like that. All right, so the design criteria then are augmented. I've just walked through the physical design criteria, then we can augment and refine that based on the biological criteria. So we worked with a number of fisheries biologists on this project to first identify what are the key preferences of the fish species of concern. So on the right, I'm just showing spawning habitat preferences for steelhead, but we have the same for spawning and rearing for steelhead, chinook, bull trout, cutthroat trout. So we can start to see, what criteria are optimal for these species, and where can we fine tune our stream design to land within those optimal criteria. Now, obviously, we can't turn every reach into a spawning reach. That's just not geomorphically appropriate. But where we can, we've worked with the fisheries biologists to optimize our design to best meet these preferred habitat conditions. And so that's this last step, the refinement of our design based on the various biological objectives that we've identified. So certain reaches are suitable physically to meet the biological criteria for spawning chinook, and certain reaches are not, but maybe they're suitable for rearing. And so we've gone through and identified those and optimized our design to the extent that we can for those biological objectives. All right, so halfway through presentation, I want to talk to you now about some examples. So we've got sort of 3 examples that I think are emblematic of the design overall. I'm going to go from downstream up and talk first about the Yellow Pine Pit restoration of the East Fork, the South Fork, the Salmon River. Sometimes I just refer to it as the East Fork, so apologies if that's confusing. Next would be Blowout Creek. You can see Blowout Creek on this image is this tributary. It's actually the East Fork of Meadow Creek, but it's called Blowout Creek for a good reason. I'll show you that. And then lastly is Meadow Creek, the tailing storage facility and the restoration of Meadow Creek on top of it. So starting with the East Fork over Yellow Pine Pit, showed you the image before of the Yellow Pine Pit, as you can see on the left with the cascade flowing down into it. Here's an image. Not very many people have actually walked down the waterfall. Luckily, I have. So here's just a picture of it from the top. Looking down, you can kind of get a perspective that's a little bit different, how big those boulders are and how steep that really is. So our design for the Yellow Pine Pit, like I mentioned, during mining, there would be a tunnel that goes around the west side of the Yellow Pine Pit that would provide passage for, on the order of 10 plus years, after which the Yellow Pine Pit mining would be complete and mine waste or development rock from other locations would be used to completely backfill the Yellow Pine Pit up to the water, up to a restored floodplain elevation and beyond. So what you see in the image on the right is the green area is that restored floodplain that we're going to be, that we've designed. And the orange areas represent areas that are actually backfilled even higher than that. And so that backfill material is basically like the overburden rock from mining. And so it's large boulders. It's akin to bedrock for all intents and purposes because it's such large boulder material that it's not readily movable by the stream. And so it will effectively define the new boundary of our valley bottom. So we actually worked with Perpetua's mine plan team to create this sort of S-shaped floodplain rather than a straight line. If it just went straight, the floodplain would result in a stream over the top of that would be relatively steep on the order of like 5 to 6% gradient, which is really pretty steep. But by creating this more sinuous floodplain, this S curve, it lengthens the floodplain and allows us to lengthen the stream, which reduces our gradient to on the order of 4 to 4.5%. It's just a steep area in general, but 4.5% is a lot easier for fish to navigate up and through than 6.5, and certainly a lot easier than the 30% gradient that's there at the Yellow Pine Pit now. But the other thing this shape allows us to do is incorporate these 2 tributaries. So you can see coming in from the right is Midnight Creek, which is labeled as MNC, Midnight Creek reaches 1 and 2. And from the left is Hennessy Creek. Those 2 streams currently do not have any fish use. There are no documented fish in those streams, but they are cold water tributaries that are perennial. And as they flow onto our restored floodplain, all of a sudden now we can take a little bit of the high flow water out of the East Fork, which is shown by those little dashed lines, and that can be used to help scour pools within the floodplain that then get filled by that perennial flow from Midnight Creek and Hennessy Creek in what's called a wall-based channel, essentially concentrating flow up against the margin of the floodplain, up against that valley wall. And so that habitat that would form periodically during those high flow events would then be filled with cold perennial water from these small streams and would be used by, or potentially used by, juvenile fish. It wouldn't be big enough for like spawning Chinook salmon, for example, but as the juvenile fish move downstream, they would be able to utilize those areas for off-channel rearing habitat, which is few and far between in these headwater areas. So high value habitat. So that's an example of we're taking advantage of the conditions that we have to optimize our design to meet those habitat objectives. And one thing I want to point out too is that, like I mentioned before, with the refinements to the plan during this environmental impact statement process, one of the refinements that's been proposed and likely moving forward is the addition of essentially a yellow pine pit replacement lake. That lake, the existing yellow pine pit, although it represents a barrier to fish passage, once that barrier is removed, the lake itself actually provided a lot of valuable habitat, particularly to bull trout, but also helped moderate temperature. Essentially, water flowed into that pit lake, and over the span of a day or two, it has a short residence time, a couple of days, before it then kind of moves back out of the lake. And so what that does is mixes the cold water from the evenings and from the nighttime with the warm water from the day, and allows for a reduction in those maximum and minimum temperatures. So luckily the USGS gauges that are on site are one above and one below the yellow pine pit. So we have real world measured data from the USGS that shows this temperature moderation that occurs as a result of the yellow pine pit lake. And we're proposing a replacement lake just to, in large part, provide habitat, but also help moderate those temperatures, just like the existing yellow pine pit lake does. The last thing I want to mention for a yellow pine pit is that the stream would be restored over that backfilled material that was in the previously excavated mine, the pit mine. The pit mine has to be dewatered, thus the tunnel going around during mining. And it takes several years for that water to rebound, for the groundwater to rebound. In the meantime, we don't want the stream channel running dry, so there's proposed to be a liner buried beneath the stream. I don't want to imply that the stream itself flows on the liner. Rather, the liner would be placed well beneath the entire floodplain. So you can see the floodplain ranges from 180 to 360 feet wide, and the channel is, a tenth of that. So there's ample room for the channel to move around. And then likewise, the liner would be buried 10 to 16 feet below the stream channel, so that the stream would have ample room to scour pools and such. And that depth was based on a conservatively calculated maximum scour depth. So the liner is there to help establish, to help maintain flows in the stream until that groundwater rebounds after a few years. And here's an artist rendering of what that would all look like when it's done. You can see upland restoration in the backfilled portions of the pit that are not on the floodplain, and then the broad floodplain with the streams migrating through it. And then there's actually, you can see the yellow pine pit lake replacement shown kind of, I'll point to it right down here. All right, Blowout Creek. So Blowout Creek is named because of, as you can see in these images, there was a large sediment blowout. Historically, this meadow that you can see on the right image was dammed to create hydroelectric power for historical mining operations. And that dam failed and destabilized the slopes downstream, which have created a perennial large source of fine sediment. I considered the largest source of fine sediment for the entire East Fork, South Fork Salmon River watershed. And then in so doing, that also the stream head cut through that meadow and has drained that meadow, and it's now starting to turn more into upland type condition. So we're proposing a fix for both the erosion and sediment problem and the meadow. The restoration of the sediment issue would be fixed with this rock drain. So essentially in the image at the bottom, you can see the existing slope in the dashed line, the proposed slope in the solid line is sort of a theoretical angle of repose. So you can see the existing channel is beyond the angle of repose, and that's why it's so consistently unstable. And so we're effectively proposing to raise the bed of the channel up to this pink line that you can see here. And in so doing, we're allowing for this accommodation space for future sediment to slough off of that hill slope and not go into the stream. It would just land on the shoulders of the stream and not in the stream itself. And in the short term, the stream would flow actually underground through a rock drain, and that's the image at the top. You can see really coarse rock that's porous, so the stream, at least at low flow, would pass beneath those rocks and be further separated from sediment issues, and while vegetation is further established along those steep slopes. Over time, that rock drain would fill in with its own sediment, and the stream would be reestablished back on the top. Again, the Blowout Creek area is currently a fish passage barrier. There's not real use of this steep section by fish. The fish are either upstream or downstream of it. So having it pass through a rock drain is not considered a detriment to fish habitat over the short term, and in the long term, that actually provides a significant benefit in reduction of sediment and improvement to temperature as well. The fix up top would be to restore this meadow. You can see there's about 16 feet of incision. You can see the old meadow surface up top that's now kind of these dry grasses and encroaching trees, and the head cut channel that's set down below that. Our proposed fix there is to place a grade control at the downstream end of all of this to help raise the water surface back up to not the condition where this was used as a hydrologic dam, in which they extended the elevation of they basically built a dam that rose the water well above the meadow. We're just proposing to raise it back up to the meadow height to reestablish that groundwater table to feed that meadow. And it would function like a large beaver dam. It would slowly fill in with sediment over time and reestablish sort of new floodplain and wetland area. So you can see the various wetland, palustrin emergent shrub, scrub, and forested type wetland revegetation plan for that area once the hydrology is reestablished. Lastly is Meadow Creek. As I mentioned before, within Meadow Creek would be the proposed tailing storage facility. This image shows a number of historical impacts that have occurred in that area. So it's definitely seen its fair share of impacts. And for the restoration, we're showing, like I mentioned, a stream restored on top of the tailings facility that then drops down a steep gradient down to the valley floor. And so where there's accessible habitat for Chinook and steelhead, that down on the valley floor, that's where the stream design has been focused there. Up top on the tailings facility, we've included habitat for what would be isolated population of resident trout up here. And similar to the other designs, we have a broad floodplain and a narrow stream corridor. So the stream is on the order of 12 feet wide, and the floodplain corridor is 90 to about 200 feet wide. And that's what's shown in the green. So you can see the whole floodplain corridor on the broader tailings facility, and the stream, a highly sinuous meandering stream with a broad floodplain. And I just want to point out that at the upstream end of these three tributaries to Meadow Creek, the stream floodplain corridor is proposed to expand greatly in this sort of flare to accommodate future alluvial fans. As we know of alluvial fans formed at the end of the last ice age, where channels were confined and then opened up onto broad, low gradient areas, and we would expect the same here. So we measured those existing alluvial fans that formed after the last ice age and provided at least that much storage space in each of these locations so that future alluvial fans can form and the channel can remain within this defined corridor. And all of our hydraulic calculations that we've done have predicted that we'll be able to maintain a gravel bed in the upper reaches that are a little bit steeper and kind of a sandy gravel bed in the lowest reach, which is the least steep. So that's reach MC1E. And at a bankful discharge, we're calculating a 7 millimeter grain size. So that's on the order of really small gravel. So again, that should be suitable for spawning and rearing of those resident fish that we'd expect in the area. And like the East Fork through the Yellow Pine Pit, a channel, stream, and floodplain liner is proposed for this area as well. In this case, to separate groundwater that might be that would be in contact with tailings from groundwater that is not in contact with tailings and is that hyporheic groundwater that would be near the surface of the stream. So again, we've got a floodplain, the entire floodplain would be lined at depth so that the channel has room to migrate laterally and to scour pools. So you can see the various depths. It's not as high a gradient, high a stream power in this reach, so the depths of the liner would not need to be as great. But we anticipate, if anything, deposition is going to occur in this reach since it's relatively low gradient. But in the short term, we need to accommodate for a potential scour. So the liner would be buried at depth across the whole floodplain. So as the stream migrates, it's not going to interact with that liner. And then here's this image I showed you before of what that would potentially look like. This is that restored stream example from the Lemhi River watershed. Okay, so last couple of slides I want to walk you through are how we're going to evaluate the function of all of this. So this is based on watershed conditions indicator matrix that was developed by the U.S. Forest Service in cooperation with other agencies that evaluate these 17 elements plus some additional fish use elements that we added. Essentially, what we've done is several groups of people have been measuring these conditions at representative sites throughout the project area to establish a baseline condition. And based on our stream design and a handful of numerical models, we've calculated how many of these conditions will change throughout the life of the mine and the rest of the proposed restoration, and then tabulated all of that in a large spreadsheet. That tabulation has occurred over reaches, just like the stream design, but in this case, the reaches have been refined to accommodate any potential change. So where the shape of the stream may change over time, we need to make sure that we accommodate that. And so we have a refinement of all of our stream reaches to make sure that there's a consistent comparison between existing and proposed conditions. And then lastly, that gets tabulated following this little equation. Essentially, we have a functional index. That's the quality from those, I'll just go back, from these elements. We measure all of these elements, they get evaluated, and that's tabulated as a score of 1 of low function, a 2 of moderate function, and a 3 of high function. Those all get tabulated per reach and created, and that results in this functional index or a quality score. And then to provide also quantity, because we want to evaluate both quality and quantity of habitat, we include the length of the stream and the stream order. And because we have some stream orders basically like the size of the stream, but non-perennial streams, our stream order is 0. We don't want to multiply by 0, so we say it's stream order plus 1. So now we have a quality and quantity component that go into this functional unit. And those were tabulated for all of the reaches across the entire project area for all of the years proposed in the mine life. So the years are at the bottom. We start in negative years because that's construction of the mine. The mine goes into operation at year 1, and that's where the positive years start. But basically 1 year per box. And then we have all of those functional units that the quality times quantity are added up. So the baseline here is 0. If we start at whatever the conditions are today, you can see there are a number of impacts shown in red that would occur early on, and then various other impacts throughout the mine life, resulting in a number in this deficit. And then we have all of our restoration that we're proposing, and a number of these things we propose to do as early as possible so that we can offset those early impacts. And so you can see the restoration components kicking in here is the green line. And then the net difference between the two is the blue line. So that's essentially the end result. And so you can see the project has sort of a net deficit over time for a number of years. And then as more and more mine features are reclaimed and restored, that benefit starts kicking in more and more. And we end up with a product of surplus at the end of the day, which was our objective. That's what Perpetua tasked us with doing, is developing a stream design that would end up with a net benefit. And so this is how we've measured it. All right, so that was a lot of information. I went just a couple minutes over, I apologize, but I want to open it up to questions. Shelley, I don't know what's come through the line or not, or what you've got for me, but I'm happy to entertain any questions.
Sure. Can you talk a little bit about how this project is different than other restoration projects you've seen or worked on?
Sure. In many instances, it's not, and in other instances, it is. It's not different from the stream design perspective. We tackle every stream design the same way. That same process I walked you through of identifying the reaches, evaluating reference conditions, empirical formulas, and literature reviews to make sure that we can develop a geomorphically appropriate functioning stream that then is optimized for the specific species and habitat types that we're trying to achieve. So in that regard, it's exactly the same. So the only real difference is that in this case, rather than restoring a stream over the top of a pasture or some other impacted surface, we're restoring the stream over the top of a mine facility. So, that's a little bit different in that there's extra precautions taken, thus the stream and floodplain liner to help, add a layer of protection to separate waters that are in contact with materials that may be contaminated from stream waters that are not. So I think by and large, it's the same process with just a few added elements of sort of risk prevention.
So going off of that risk prevention, you talked about having that coconut layer, some riparian habitat. How long will it take for that riparian habitat to take over and just become a natural thing?
Yeah, good question. It really depends on the type. Each reach has a different planting plan, so there are different species proposed. And then also the type of bank treatment. So some of the banks will have rock in them, unquestionably, because we're working in steep areas where rock is totally normal and natural. Other areas, like the really low gradient areas up on the tailings facility, for example, that won't have rock built into the banks. And so we'll be completely reliant on our bioengineered bank stabilization until the riparian vegetation can take hold. Those sort of fabric encapsulated soil lifts were used in previous restorations, actually on Meadow Creek by the Forest Service, that are a little over, I think, 12, 13 years old now. And they're still there. You can actually still see them. They're starting to tear and become decomposed. And the alder and willow vegetation is on the order of, the alders are like 10 to 12 feet tall, and the willows are like 5 to 6 feet tall. And so their roots have really started to take over the lion's share of the stability, the stabilization along those banks. So using that as an analog in other projects that we've done, the growing season is less up at this elevation, but also the decay rate is lower. So it's, maybe 10 to 20 years is what we would expect before those fabric layers are essentially no longer functional, and that the root vegetation would take hold. And the willows and alders will grow up to be relatively mature within that period of time. The spruce trees take 60 to 70 years to grow to full height, but their root mass will be pretty substantial after 10 to 12 years.
I do have another question that came in. Are the restoration features self-sustaining, or will they require ongoing post-mining monitoring and maintenance?
Good question. They are designed to be self-sustaining, but there is, kind of the belt and suspenders approach to this whole project, just to make sure, it's a high-profile project, and to try to mitigate risk, we've included, a substantial adaptive management and monitoring program. So we're proposing to plant riparian vegetation that would ultimately, mature into mature woody vegetation and provide large woody debris recruitment. Of course, that's going to take time. So we're also proposing to add a lot of woody debris. But we're allowing the stream to migrate within that corridor that's amply, substantially wider than the corridor that the stream has to migrate in now. So the short answer is, yeah, it's self-sustaining, but if the design objectives aren't being met within the first several years of monitoring, there's an adaptive management program that would be in place to go and address those issues. Likewise, if there's some unanticipated impact, like a fire in the watershed, that might affect how things change. Again, we think our stream design is the most resilient type of stream design you can provide, because it emulates a natural system that would evolve with a natural disturbance like a wildfire. But there are unexpected occurrences, so there is a monitoring and adaptive management program that would be instituted after the restoration program.
And will the restoration measures be included in the financial assurance for the project?
Boy, Shelley, I turn that question around to you. I assume yes.
I am not the appropriate person to answer that, but I would agree with you. I would assume yes.
Yeah, from what I understand, that's well outside of my wheelhouse, but from what I understand, the restoration measures are all included within the financial assurance, and doubly so because they're assumed to be accomplished using sort of normal equipment rather than mine fleet equipment. So the cost is greater for using sort of day-to-day excavators versus the large scale type machinery that would be on site from the mining project. So I think the answer is yes.
Great. And last question, I think, for you. Recently, there has the UFS released a statement with some refinements to our project that they are taking a look at. Can you talk more on how those newly released refinements affect the stream restoration side of things?
Sure. And again, I won't be able to touch on all of these, nor am I aware of even all of them, but the key ones that are germane to the stream restoration are like the removal of the Fiddle Creek development rock storage facility. So that was, I pointed it out in an earlier slide, there was a large development rock storage facility that would be in the Fiddle Creek watershed. That's now been removed and replaced with a substantially smaller, essentially topsoil storage area. And so that greatly reduces the impact on streams on Fiddle Creek. Likewise, there have been a number of refinements proposed to improve temperature because during the draft environmental impact statement, temperature was identified as a significant concern. So a number of things have been done to the proposed stream design, including the addition of that yellow pine pit replacement lake. As I mentioned before, the USGS gauge data that measures both stream flow, but also temperature above and below the existing yellow pine pit show that that pit basically buffers really maximum temperatures. So those high and low temperatures on a daily basis. And without that lake in place or something comparable to that lake, we just can't achieve the same temperature, the same sort of level of maximum temperatures in the summer. Our temperatures are coming in too high. So we're proposing a similar feature to help buffer those temperatures, among other things, refinements to the planting plan. We've proposed some improvements to some of the smaller tributary streams like Garnet Creek to provide further restoration of areas that were proposed to be impacted. And I think the other important thing is a handful of key restoration components got moved up in the sequence. So for example, Blowout Creek restoration was previously, portions of it were proposed to be later in the mine sequence, are now proposed to be earlier in the mine sequence. So those are some of the key stream related changes or refinements to the plan.
Excellent. Well, thank you very much. And for those of you guys who are interested in hearing more about those refinements, we are going to do another webinar on August 12th, I believe, with the permitting manager here at Perpetua, Dale Kerner. So please go onto our website at perpetuaresources.com and sign up for that webinar if you're interested in hearing more details on all of those refinements. Thank you guys so much for hanging out with us. We really appreciate you taking an hour out of your day to learn more about our project, and we hope to see you again soon. And thank you, Rob, for presenting. We really appreciate it. Have a good day.
Pleasure.